Hello, everyone. It's 1 p.m. Eastern, and that means it's time to begin our 81st CoCoRaHS WxTalk Webinar. Wow, 81 of these we've got in the books already, or will have after today. A very warm welcome to all of you joining us today. I'm your host, meteorologist Henry Regis. Running the technical side of our program is our very own Noah Newman. We're coming to you live from sunny Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we are recording today's talk, and it will be available later this week on our website. All of our WxTalk webinars are sponsored by the generous donations from listeners just like you. Well, today's webinar will take a look at the ocean and atmosphere, how they affect our weather, specifically the Pacific coast of the U.S. Many of you are familiar with the coastal sea breeze, and we'll look at that as well. Our guest today is Eric Skyllingstad of Oregon State University, located in Corvallis, Oregon, right there, not too far from the coast. Eric originally is from Cincinnati, Ohio, that area there. He received an undergraduate degree from Oregon State University and did his graduate studies at the University of Wisconsin in Madison. Eric worked for 10 years at the Pacific Northwest National Lab, doing research on the atmosphere boundary layer, and then on to Oregon State University into a research teaching professor position, where he's been studying ocean-atmosphere interaction for the past 25 years. In his off time, Eric likes to snow ski, as many of us do, and he likes to forecast whether there will be snow or rain to ski in, as you do get a mixture out there in Oregon. He also likes to fish in the Pacific Ocean. Maybe he can tell us a couple of fish stories on what he's caught. And again, that can be a whole adventure in itself out there in the Pacific Ocean. Well, let's give a big CoCoRaHS welcome to Eric. Eric, it's great to have you with us today.
Thank you.
I'm going to start off with a question we ask all of our guests here, and that's, how did you become interested in weather? Where did that begin?
Well, growing up in Ohio, we didn't get a lot of snow, but we got some snow. And when I was younger, I really liked to get out of school when it snowed. So in order to basically understand it better, I just got interested. And that was probably the start. One other thing that really kind of caught my interest was severe weather. And in particular, there was a very large tornado outbreak, I think in 1974, the Xenia tornado. And that, I remember that day very clearly still now. There was insulation falling out of the sky above our house, and that was very dramatic. So those were the things that really got me interested in meteorology.
Wow, yeah, I remember that outbreak there in April of 74. That was quite a, and you guys there in Ohio bore the brunt of a lot of that. I've got to ask you, the slide you have up, the bridge in the background, can you tell us what bridge that is?
Yes, this is a picture from my fishing boat that you can kind of see the back of it there, the stern. And we're looking towards Newport. And this is US 101 going over Newport Bay, or the entrance to the bay. And it's one of the bridges that was built back in the 1930s during the Depression, all along the West Coast. So there's a number of bridges kind of like this one. They're kind of iconic for the West Coast.
Yeah, it's a great shot. Can you tell it what type of fish do you catch when you go out there in the Pacific?
So in this picture, we're actually not catching fish. We're catching crab. That's what the davit is on the left side there. We use that to pull up crab pots. But fish we catch would be out in the open ocean, primarily our salmon. There are folks that go for halibut, and then there's people that fish for other sort of pelagic open ocean fish like tuna, but you have to go further offshore for those. I typically have a small boat, so I stick within a couple miles, maybe out to maybe 5 miles from the beach. I like to be able to see land.
And for the salmon, do you fish deep for those? Are they a surface fish? I'm not familiar with that. I'm just curious.
You can do two different things. Most of the time you use a gear called downriggers, and what those do is bring your lure down to some depth that you define. It has a wire, and it basically has a little clip that holds the fishing line on it, and then the lure goes behind the boat some distance, And you can vary the depth, usually not much deeper than maybe 150 to 160 feet. That you're targeting different fish depending on the depth. If you want to catch coho salmon, you want to near the surface. Sometimes you don't even need to use a downer. You can just fish off the back of the boat. If you want to go for Chinook or king salmon, you go deep, typically 60 to 100 feet. The two fish mix together, but a lot of times those depths are the only way you'll get one or the other.
That's really neat. Well, thanks for sharing that with us. I'm going to turn it over to you now, and we look forward to your presentation. We'll take questions, folks, when Eric's finished with the presentation here. And again, we really appreciate you being with us today.
Sure. Okay, so I'm going to go ahead and just go into my outline here. What I want to talk about today are a couple different things. I'm going to start out with a little bit of a seminar style or classroom style, talking about what drives the wind. And I want to look at the different forces that we have in the atmosphere that lead to basically the movement of the air. So we'll do that first. And then I'm wanting to go over that kind of basic knowledge so that we can make some sense out of the other things that I'll be talking about having to do with the West Coast, spreading out a little bit to other areas. And then I'm going to look at basically our two seasons and the type of weather we have here. Typically, the Western United States has somewhat of what you might call a Mediterranean climate. And what that really means in my mind is we have kind of two seasons where there's a fairly different weather pattern depending on one or the other. Winter and summer are quite a bit different here. And then I'll finish up with a little bit of talk about our specific right on the coast, upwelling, and how that affects our weather here. And then finish up with a kind of a topic that I'm interested in is what gives us our kind of consistent patterns. And in particular this year, we're having a very wet, cold spring, and people are starting to really grumble. And it's probably tied to tropical connections, and that's what I'll finish up on. So we'll jump into it here. And so here are the things that we're going to talk about first. We'll do a little review of fluid dynamics. We're going to talk about pressure force. I think everyone's fairly familiar with the weather maps showing high pressures and low pressures. We'll talk about that. We'll talk about the Coriolis force, which is something that, if you haven't heard about it, it's the other, I would say, the other important thing that happens for fluid dynamics on the Earth and basically any rotating planet or rotating system. And we'll just kind of describe it and I'll show a little video. Then we'll bring in some other things that affect the flow. These are somewhat more secondary for larger scale things, but still very important. The first one is surface friction. Everybody kind of familiar with that. If you have something moving over a surface, it will slow down. It loses momentum to the surface, and that will make it stop. Air does the same sort of thing. It wants to slow down, or it loses energy and it loses momentum to the ground or to mountains. So it's pretty important. And it varies quite a bit between land and water. And then the last thing I'll bring up is the centrifugal force. This is something we're all familiar with. Somewhere along the line, you were swinging a ball around above your head, and you let go and it took off. You had on a string, a tether ball. So that's the centrifugal force, and air that's moving in circles or around something is going to have that same kind of force. It's not really a force. It's the inertia of the object, the fact that an object in motion wants to keep going the same way. And it is perceived as a force because it feels like it's pulling away from you. So here's pressure force, very simple little diagram showing you a couple of tanks. And if you had one tank with lots of water in it and one with less, you're going to have higher pressure at the bottom of the tank with water in it and lower pressure in the other one. It's just the weight of the water. And that will force water from one tank to the next. And that's a pressure force. This is, if you were to look at meteorologically, this would be like air over cold water on the left side, that high pressure, and then warm air on the right side. That has a lower pressure. So then it acts to move, in this case, water from one side to the other. we can draw a real simple diagram in the atmosphere, and I'm showing here a high pressure and a low pressure. And the lines you see going down are lines of constant pressure. We call those isobars. And there's two different pressures, which are here listed in what are called millibars, but we also use a term called hectopascals, hundreds of pascals. And those are just telling you what the pressure value is at that level. You don't really need to know much more than that. And what we can see here is that there's a force that wants to push or have the air go from the high pressure to the low pressure. So that's sort of the basic setup of most weather systems. You have a high and low pressure, and you have some sort of gradient of pressure between them, or some change in pressure. Here's basically a plot taken from a model run. This was from yesterday, and it's showing the West Coast. Let me get my pointer going here. The mouse over here is showing the West Coast right along through here, and there was a high pressure offshore, and then it's low up in the Gulf of Alaska. It's a very typical pattern, and I just drew some arrows on here showing you, well, this is the direction in which the pressure wants the air to move. So it wants to move away from the high pressure and towards the low pressure. So that's your basic kind of principle. What has pressure patterns on the ground? You've all seen maps like that. Now here's another sort of schematic showing, well, weather isn't just at the ground, it extends all the way through the atmosphere. And so we want to know what's going on above us also. And for that, we look quite often at surfaces of constant pressure, and that's what this is showing. And in those cases, just the change in the surface height tells you something about whether it's a low pressure or high pressure. So for warmer air is expanded because it expands when it's warm. Colder air contracts. That's just how air works. Most of us are familiar with that. And because of that, you'll have different heights in a pressure surface. And over here where it's cold, that would be a low pressure system. And over here where it's warm, that would be a high pressure system. So here's a plot, West Coast again, same sort of time period. This is Sunday. And what this shows is the height of the 500 hectopascal surface, which is basically halfway through the atmosphere. So the surfaces are around 1,000, and 500 hectopascals is about halfway up through the atmosphere. And you can see there's different patterns here, just like we had at the surface. And other things you can note here is that the cloud systems tend to follow these different disturbances in the height field, or you can think of it like a pressure field, but it has the same kind of effect. And then the other thing you might notice is that there's these wind bar things drawn on here, and those are pointing in the direction that the wind is blowing. So, and then they have these little symbols on here tell you the speed. So this would be like 45 knots, the big flag's 50 knots. So the wind you can see is blowing along the same lines of the height. So it's not going towards lower pressure. Except for maybe a few little places. And this is up high up, so 18,000 feet or so. And so the air up there is basically not going across the pressure surfaces. And why is that? So that's where we want to know about the other forces, and in particular, the Coriolis force. The Coriolis force is essentially just the movement of air on a rotating surface. Again, wants to follow a straight line. So the surface is rotating, and the air, since we're on a rotating reference frame, to us, it looks like the air wants to go to the right. And that's just because we're on a rotating planet. And in the northern hemisphere, it wants to go to the right. In the southern hemisphere, it's like flipping upside down. It wants to go to the left. Now, that's all I'm going to say about the southern hemisphere. So for our purposes, you can think of the Coriolis force as a force that wants the air to go to the right. That's the main thing. And I have this little video here that I was going to show. Hopefully this will work. Giving an example. This just is about a 3-minute little, well, maybe not. Let's go back there again. Okay, that's a 3-minute little video. I think I'm going to shut that off. And it shows these two guys on a turntable throwing a ball. And I think it's a pretty good visualization of what the Coriolis term. So here it is, they're just throwing the ball. This is what people at MIT do in their spare time. Okay, now we're going to spin it. And they're spinning it like the Earth. So when he throws the ball, it doesn't go straight across, right? It looks like it's curving. Now they'll show another picture here in a minute. There we go. So when you're looking down on the planet, you see the motion of air. That would be the ball. In a minute, they'll draw a line, and you're going to see that it actually is going in a straight line. So that's an air parcel on the planet. That's what it's doing if you were standing out in outer space looking down and watching that air parcel move across the planet. Now, from the rotating frame, it doesn't look like that, right? So here's the rotating frame. It wants to go to the right. It looks like the ball is going to the right. And that's basically what air parcels are going to do on the planet. They're going to travel to the right because they're just conserving their motion. They want to go in a straight line, and we're rotating, so it makes them appear as though they're going to the right. Okay. Watch it from one more angle, and then we'll move on. Yep, there it goes, to the right. Okay, so what happens on the planet? If you were to take that pressure gradient we had before, and start with some little bit of air down here in the high pressure area, it starts moving, in this case, it starts moving north, but because of the Coriolis force, which is proportional to how fast it's moving, it starts moving to the right. And what you see here is as that air moves north, it's moving more and more to the right. The pressure force doesn't change, it's the same. And then at some point, that Coriolis force equals the pressure force. And that balance that you see in this little cartoon is what we call geostrophic flow. So when we were looking at those maps a minute ago, we saw this same kind of thing. Here's another schematic showing you, this is kind of a more realistic schematic showing you the pattern of winds and 500 millibar or hectopascal contours, and just drawing on top of that the Coriolis term saying go to the right, and then the pressure gradient force saying go to the left. Okay, so that's our basic geostrophic flow, and you can kind of look at large scale weather and say that most large scale weather has a flow pattern that is close to geostrophic, and you'd be pretty much correct. And that's great. But there's other things that are going on, and this is, I'll just show real quickly. If you have a rotating system like this, a low pressure or high pressure, you have that balance, but you also have the centrifugal force. You have the parcel itself of air, or the air movement. It wants to keep going straight, not just because of the rotating planet, but because it's rotating around some pressure system. Okay, so that we call a centrifugal force. And for most large scale meteorology, this force is important, but it's not something that we, it's a more secondary thing. As it turns out, it actually is pretty important for storms, and for vertical motion that gives you clouds, but it's typically smaller than the pressure gradient force or the Coriolis force. There are exceptions to that. Well, let me go back to this map right here. Again, this was from Monday here. If you look out over the water, this is surface pressure. You can see that the winds are pretty much parallel to the pressure lines. So the flow is acting a lot like it's in geostrophic balance when you look out over the Pacific, the few stations that we have. And but on land, that's not the case. On land, you see these arrows are pointing, particularly, let's look up here in Canada. These wind vectors or wind barbs are actually crossing the pressure lines. They're pointed towards, a little bit towards lower pressure. And that's because of friction. That's because we've slowed down the wind, and we're changing that balance. So we're not seeing the effects of the centrifugal force here. We're really seeing the effects of the ground. When do we care about the centrifugal force? Well, here's two good examples, hurricane and a tornado. Coriolis depends on both speed and time. And both of these cases, you have a pressure gradient that's very strong, and you are only, you're basically only moving in a very tight circle. So what ends up happening is you have a very large centrifugal force relative to what the Coriolis force would be. So you get a different balance. You get a balance between that centrifugal force and the pressure force. We call that cyclostrophic flow. Here's an example of a hurricane. I think this will work, yeah. Hurricane Irma, this was one of the first really well observed from the new satellite systems hurricane, and they remapped it so you could watch how it evolved over time. I thought it was just a fascinating little video, but I drew on here a line with about 200 kilometers is roughly the scale of that center. That's very small. So air parcels have a radius that they're turning around that's very small. And that makes their centrifugal force, this outward directed force, very large. So that's the balance that's occurring here. It's the low pressure of the hurricane and the rapid spinning of that flow around the center. So here's surface friction. This is the last one we'll talk about. And basically, friction is just going to act to slow down the flow. And as soon as you slow it down, you're going to change two things. You're going to change the Coriolis term because it depends on the velocity of the air. And you're also going to change that centrifugal force. But really, the thing that we're interested in here is how it changes the Coriolis force. If we go back to that diagram I had earlier where you see the balance between pressure gradient and Coriolis, that is our geostrophic wind. Now we've reduced the speed by friction. So this shows it up high, say, 3,000 meters. Now down at the ground, friction is slowing down that wind speed. That weakens the Coriolis force. And because it's weakened that, the air parcels are more likely to go towards lower pressure. And so that's what the winds do. When we looked at that surface map earlier, you could see those vectors or those wind directions were heading towards lower pressure. And here that is again. So in particular, up here in Canada, you can see the flow that's directed across the isobars. This is pretty important in terms of how it affects our flow along the West Coast. And I'll go into a couple of examples where it's not so much friction, but mountains. I mean, you can view a mountain as a big rough element in the atmosphere, just like you would friction that you're thinking about when you have, say, air going over your lawn versus a smooth road surface. So we'll just do a quick thing on the coastal winter weather because I wanted to point out two different things that I think are kind of important for what we have here on the West Coast. We have a little different kind of weather than the Midwest because of the ocean. And so that's what I'm going to really be pointing out here. So we have storm systems just like everywhere else, where we'll have a storm come through with cold fronts and warm fronts, low pressure system. That's pretty typical. But we also have something that comes in after the cold front. And if you live in the Midwest, you know that typically when you have a cold front go through, it clears up. It might get cold, but it clears up and that's it. You're done. You're just going to have clear skies. Actually, usually a lot of times pretty nice weather. Wind might blow pretty strong at first, but other than that, it's not a bad thing. I mean, in terms of sunshine. Here, we get a different thing. We get convective showers. We will have days of convective showers. And the reason for that is because that cold air that's behind the cold front is going over relatively warm water. And so it fuels convective showers. And I say much like lake effect snow because that's what fuels lake effect snow is cold air moving over warm water. It picks up moisture, it evaporates, and then you get precipitation events from that. So without the warm ocean, we wouldn't really have these showers. I'm just going to walk through this little sequence. This is from last Saturday, and there's two different things going on here. Well, there's actually three. There's a storm out here in the middle of the Pacific, and you can see its sort of shape. This is developing what we call developing baroclinic wave. And then over here, where we are on the West Coast, or where I am, there's strong flow coming in from this kind of upper level disturbance up here, but there's not really a cyclone. There's not a strong cold front and all that goes with it. It's just a little disturbance, and lots of convection behind here. What's shown on here are the height lines of that 500 millibar, and then also the temperature. And you can see here it says -36, so it's pretty cold at 18,000 feet. And then down here in the tropics, it's like -8 or -12. So there's a big gradient of temperature across there. That cold air is basically giving you an atmosphere which is warm on the bottom and cold above. And so the warm air will rise and form convective clouds. And that's what happens. They produce a lot of showers. The storm, on the other hand, is a more organized, large-scale feature. And if we walk through, we'll watch that storm just sort of spin up and, whoops, went too far, out with that trough out there. Whereas where we get this little disturbance coming through in a lot of convective rain. And I'll go on to the next one.
Eric, let me ask you a quick question. Are those
Sure.
are those basically just showers or thunderstorms that with the convection that you get there?
We can get some lightning, and typically the lightning is actually offshore. It's because it's more unstable, particularly in the winter because of the warm water. However, I would say it's very rare, and the reason why is because it is these very cold temperatures at relatively low elevation. So the tops of those storms are 18,000 feet. So they have to get above that to get enough charge separation, I think, for lightning. And so lightning is kind of a rare event. Does that make sense?
Yeah, thanks.
Mm-hmm. Yeah, in fact, I look for lightning a lot. And for those of you that look at satellite data, you can pull that up with, I should give a list of all these sites to look at, but you can pull up lightning data now pretty easily, which is very nice, real handy, especially out over the ocean where you don't have any other way of knowing if it's there.
Maybe we can include that on our webpage of resources. We'll post that this week.
Okay. Yeah, I have a little thing I can put that on there. Okay, let's see. So we step on through now. This is right now, well, not right now. This is a few hours ago. And you can see I'm in Corvallis. I'm sitting down here in the middle of this, what I will call rain shield. And this is a cold front that's coming through. And once this cold front comes through, now if this were Illinois, none of this would be back here. This would be probably clear skies back here. Or if anything, it'd be low clouds, some small clouds, nothing to really write home about. For us, that's going to give us rain showers for the next day and a half. We'll get probably half of the rain from the storm, the whole thing, from those convective showers. So it's really a big part of our precipitation in the wintertime. And it's all there because you've got basically all this warm water, relatively warm water, that's giving up moisture to the atmosphere, which then gets dropped on us. Okay. Okay, so I'm going to move now more into sort of the local scale wind systems, and this is where terrain and friction are going to have a fairly significant impact. This little figure here or this little satellite picture, I posted this. I noticed it, I don't know when it was, a few summers ago, but there was this really nice eddy down here and in this stratus cloud deck. This may actually even be fog, don't really know. And you'll see these along the West Coast when you have flow coming down the coast, and it interacts with basically mountains that are along the coast, not so much the shape of the coast itself, but mountains that are obstructing the flow. And you can't see that obstruction, but it shows up in the cloud field. So it's kind of interesting. This would be something where it might be a somewhat cyclostrophic. It's not Coriolis. It's too small, just as a note. So where are some places where we worry about or think about effects of friction? One of them is the Columbia River Gorge. This is up between east of Portland, and the Cascade Mountains basically are aligned north and south, and right through the middle of them is a river. And so you drop down from something like a sort of a ridge line of 4,000 to 5,000 feet down to sea level. And in fact, this really is sea level. Before they put the dams in, you used to see tidal fluctuations in the river level, way up into the gorge. So it's essentially sea level. And when you have a gradient set up with high pressure over the west and low pressure over the interior of the state, you'll set up a geostrophic flow, which says, well, the wind should be blowing north. But because of the terrain, the wind actually will go through that gorge, and you get some pretty good winds, to the point where some of the locations down in here are known for windsurfing. It has this really nice aspect where the wind is blowing upstream, which means that if you're windsurfing, you go upstream, and then when you want to go home, you just drop your sail and float back to wherever you started from. So that's kind of nice, and it's very popular. So these two locations are about 90 miles apart, and you can have some pretty significant winds blowing through there. Another example of sort of a local effect are sea breezes and land breezes. And I'm going to show first, well, before I get to the sea breezes, land breezes, I'll talk about another place where we see significant channeling of the wind. And if you look on both of these plots, this is from a few years ago, I'm showing the Willamette Valley. That's what's in that box. This is from this morning. And there's this front coming through that I showed you earlier. And you can see all these vectors, all these wind barbs are cutting straight, cutting straight across the pressure gradient right here in the Willamette Valley. And that's pretty typical channeling, because we have the Coast Range between the valley and the coast, and then we have the Cascades to our east. And so the winds are basically, because of friction, really, from those two mountain ranges, it causes the wind to be aligned and cross the pressure gradient. And that can cause stronger winds than you would get otherwise. This is really noticeable on the coast as fronts come in. I'm showing over here a plot of today. As that front comes in, and this is wind gusts, so we're looking at pretty high wind gusts up to between 50 and 60 knots. So that's pretty strong. That's like a 65, 70 mile an hour wind gust. And you notice it's got this sort of tongue of high velocity, gust velocity, extending up the coast. And that's blocking by the Coast Range and causing the wind to cut across the gradient again. And we call this the coastal jet. Every time we get a decent sized front coming through, that will set up. And it, of course, is very important to mariners. They would like to know about this, because you can get what seems to be pretty decent conditions turn very bad very quickly as this sets up. And then it will move, it'll essentially dissipate as the front moves on shore. And it will not be, it's not an indication that we're going to get a big windstorm here. It really is focused just on the coast. So that's our kind of winter, just a brush of our winter weather. I'll talk more about our summer weather, because in some ways our summer weather is even more unique than the winter. The storm track's pretty much gone. It's up north. So our weather is dominated by this land-sea temperature difference. And again, the biggest issue, or the biggest thing, is high pressure over cold water, cool water, and low pressure over land. And then there's some secondary things we'll talk about, like upwelling, which make the water even colder. So these are the main actors, these two pressure systems. And in general, for coastal areas, in particular in the summer, you'll get sea breezes. And what that means is that over land, you'll have warmer air, and warmer air basically expands. Just as we know, warm air, that's what it does. It has less density. So warm air expands, and what I'm showing here are pressure surfaces, these lines that go across. So that air expands upward, whereas over the water, you can think of those same pressure surfaces being contracted because it's cooler. So that basically sets up a pressure gradient between the water, high pressure over here, and low pressure over here. And then the reverse is true above, say the top, usually it's the top of the boundary layer that we're looking at here. So the top of the boundary layer is higher over land and lower over the water. And so that drives the flow back towards the ocean. So we get a sea breeze, a breeze that goes towards the land near the water, and then it's return flow somewhere above. Okay, so that's a sea breeze. And this happens all over the place. It happens pretty much on all our coastlines. Here, it can have a pretty big control on how warm it gets here in the valley, because what will happen is if you have the right sort of large scale gradient, then the heating in the valley will be enough to draw a sea breeze over the coast range and cool us off in the afternoon. Sometimes that's really nice to have happen. Other times it drags in a bunch of stratus clouds and kind of ruins the day. But for the most part, we don't really have continuous heat waves because of these sea breezes. Land breeze is the opposite. It happens at night. This is sort of I'll go back to my fishing background. The land breeze is kind of a nice thing if we're under a typical summer condition where we have strong north winds on the coast, so strong that you don't want to go out on the water. Those relax at night, and the reason they relax is because of this land breeze. You can get a flow that goes offshore. It's the opposite of the daytime, because now the land is cooler than the ocean, or at least it's similar in temperature. And when it does that, the winds relax really close to the coast within, say, 5 miles. So you can sneak out and go fishing at sunrise for a few hours, but you got to get back because the wind will pick up once that land breeze switches to a sea breeze. I'm showing this figure, again, this is from a few days ago, just to give you a really visual look at what is different between land and sea. And this right now, that's more like a winter picture than a summer picture by far. But you can see that just from the cloud pattern, that over the ocean, you have all the cellular convection out here that's fairly well, I'd say somewhat organized. Over land is just sort of like chaos, but there's lots of clouds. Now, this is all because of heating, solar heating in the daytime, and it generates a lot of smaller circulations. You can make out the Cascade Range, at least you can make out where the top of the range is. That's this line right here. There's a little bit of flow across the mountains. It's enough that you get some drying effect on the lee side. And then you can see the Willamette Valley has a similar kind of an effect. This is a rain shadow effect that we get here in Willamette Valley. We have it, and then it's very strong on the east side of the mountains, to the point where out here in the gorge, you can see there isn't hardly a cloud in the sky. So that's one of the effects we get that's on the larger scale from this land-sea difference. Here's another location completely separate from here. This is Florida. And they get a very distinctive sea breeze, and they get thunderstorms that form in response to that sea breeze. You can see the whole inner peninsula here becomes convective, and then you see all these little, these are called thunderstorm outflows, and I'm going to just show a couple of quick slides on that because they're kind of interesting. And I've done some simulations of these, but what happens is when you get convective storms like these, they have precipitation that cools the air beneath them, and that cool air, because it's more dense, it spreads out. And you can see the leading edge of that cool air forming these little cloud lines. Now, if I go back to this picture, that's what all these little cloud lines are out here in the Pacific. These are all little cold air outflow boundaries where that's what's giving you this sort of cellular looking structure where you have convection and then essentially kind of clearer conditions between these like outflow boundaries. So I've done some simulations of this, and this is one where I put a patch of warm water in the middle of a very simple model to see what would happen in this kind of a tropical case. And that patch of warm water will convect because it's warmer there. And then what happens is you'll get these outflow boundaries forming essentially squall lines, and that's where new convection forms as that cold air spreads out. You can kind of see that happening right up here as this thing evolves. So that's all in response to a little patch of water in the middle that's, maybe a few degrees warmer than the water around it. Okay. And this happens on land too, a little bit sometimes very obvious. This is in Arizona. These are this mountain range up here. This would be the area down around Phoenix. And we'll play this one. And you can see the convection, and then there's this front that just comes out and ahead of that. And all these storms are propagating along that front. And that's a cold air outflow, just dense air flowing out and triggering new convection. Okay, so another summer thing that happens on the West Coast is we get what's called a thermal trough and upwelling. This figure here is from some number of years back and shows you surface temperature along with the surface pressure and winds. And what you can see here is the Southwest is down here. It's really hot down there. This extends towards the west and actually goes out over the water. Okay, so you have what basically warm air that's extending out over the water. And that is called a thermal trough. And it fluctuates during the day, but it's essentially a permanent feature in the summertime. And it drives the pressure field. You can see the lower pressure all around that warmer air. So what's happening when it gets to the coast is you've got really warm air here, lower pressure, right next to this higher pressure system. And so you get really strong gradients. And that strong gradient in pressure will drive winds down the coast. So we have essentially the northwest wind all summer long along our coastline and extending down into California. So that is summer. It's that strong wind. We'll get what we call relaxation events where occasionally the thermal trough will extend out over the water, and then that'll kind of push the north winds offshore. Or we might have a weak storm come through and that will weaken the gradient enough so that you will get a relaxation of those winds. But other than that, it's there a lot. Okay. One thing that happens because of that north wind is what's called upwelling. And upwelling happens because the wind is blowing down the coast, so it's coming from the north here, and it's pushing the water southward. So as the water gets pushed southward, it is affected by Corvallis. It tends to go to the right, just like the wind did when it was going around a pressure system. So the water gets pushed offshore, and there's no place for water to come from except from below. So what ends up happening is you get water rising along the coast. It's getting essentially pulled up to the coast by the wind and the Corvallis force pushing the water off. On the right side, I've got a couple of figures here that show you sea surface temperature in the summertime. And you can see that upwelling starting way up here in Washington. And it's kind of hugging the coast all the way down Oregon. And then it kind of peels off and goes offshore when you get down near California. So our coastline and Washington coastline has this cold water, and we're not fooling around. It's like 9 to 8 degrees. It's like in the upper 40s quite often, right on the beach. And literally the water temperature on the beach will be 48 degrees. If you go offshore, maybe especially up north here, maybe 100 kilometers or maybe 50 miles sometimes, you'll get into water that, I don't know why it keeps doing that. You'll get into water that's quite a bit warmer, 16, 17 Celsius. It can be 62, 63 degrees. Remember earlier I said some people go fishing for tuna. That's where they go. So when there's strong upwelling, tuna don't like cold water. So they are out in they're kind of a semi-tropical fish. So they're way offshore. Sometimes that warm water gets pretty close and they'll get within, say, maybe 30 miles. But they follow that warm water around. Whereas the salmon, on the other hand, stick with the cold water. They are best caught when the water temperature is between 50 and 52. If it's any colder, they kind of go out the ways, and if it's any warmer, they go deep. So the fish follow this. Okay, so coastal upwelling. It's often associated with fog, and it's also really important. It brings up a lot of nutrients, and what I mean by nutrients is that deep water that's coming up from below has a lot of minerals in it and things in it that make plankton and other life really get started. And so you'll get these blooms of phytoplankton that goes right up the food chain and all the way up to the things that salmon like to eat and other fish like to eat. So it really does fuel a lot of the fisheries on the West Coast. So you can say the winds, are persistent northerly winds, give us a really strong fishery just because of upwelling. That's true all over the place. You're probably all kind of familiar with off the coast of South America. We talk about El Nino, and El Nino all has to do with the fact that when you have an El Nino, the upwelling off of Chile goes away. They lose their winds, and so that was always an important thing to the local fishermen because they didn't have anything to eat. Okay. In kind of recent year, well, not so recent now, but in the last 20 years, we've been able to take a closer look at what is going on with, say, the wind fields and how the coastal circulation is affected by upwelling and what affects it. And what I'm showing here is a plot of surface winds over the ocean that are observed from a satellite, a scatterometer. It's basically measuring the roughness of the surface of the water, and then they made some clever parameter, well, we call them a parameterization, but some tools to relate that roughness that you see in the microwave sensor to velocity of the air right at the surface. So it's like little waves on the surface that are ruffled up by the wind. Anyway, so this shows you a couple of different places where the wind, and this is plotted as wind stress, where the wind stress is increased in part due to these coastal capes, and really it's also terrain. So you have higher mountains that are near the water, and they have an effect that goes way offshore, right? I mean, that's hundreds of kilometers offshore for a mountain that's sitting, right on the beach almost. These winds can, as I say, vary over very short distances, so they're important for any kind of activity out over the water. We did some simulations of these, and this is our model of a very simple cape, and you can kind of see what happens as the flow goes around that cape. It accelerates just downstream from that. I'm plotting here is the wind speed and direction. Okay. And another thing that happens is as part of that sea breeze circulation, you'll get a fluctuation in the winds along the coast. And here I'm plotting data from a number of buoys, and these are full day record averages. So you're getting sort of a climatology of the wind speed and direction. And you can see up here, right off our coast here by Newport, the winds are varying, but not a whole lot. But they're still going up by, and this is wind stress. The wind stress is doubling between the morning and night. Not so much of a change south of here, but when you get down to Northern California, where you're near that cape, where we noticed earlier there was a really strong response, there's a really strong diurnal cycle where the winds the wind stress anyway is going up by over a factor of 2 between the late afternoon when it's at a maximum and the early morning. So again, remember I mentioned this land breeze effect. That's kind of this land breeze effect where things relax at night. Okay, and we model, as part of our modeling project, we looked at that, and you can really see that in the model very clearly. The early morning hours, so 8 in the morning, the winds near the beach are very weak, and then as you get into the afternoon, they spin up and get stronger, and so you get this maximum in the late afternoon down here. So you wouldn't want to go out fishing in this area in the lee of this little cape here, except for perhaps for a little bit in the morning, but the rest of the day, forget it, too windy. This shows up in the cloud fields too. So here's on the left is our simulation, very simple. And then on the right is just a satellite image showing you how the different capes affect the flow. And you can literally see the wind kind of in these clouds here. Downstream from the points, you're getting sinking air, and that essentially forces the boundary layer down near the surface and to the point where the clouds can't form. And then north of the Cape, you have the marine layer getting deeper and moving inland into these valleys along the beach there. Sometimes what we'll get to in cases where we have a thermal trough moving offshore is it'll move offshore, and that, remember I said the north wind will relax. And if it relaxes enough, it'll actually reverse direction. And when that happens, you'll get what's called a coastal surge. And you might be on the beach sitting there and it's beautiful, 70 degrees, really nice, no, hardly any wind. And a few minutes later, the wind will shift to the south and the fog will roll in, and you might as well go inside. So that's what's shown here is this case where there was a coastal surge, and it just moves straight up the coast. And basically the big problem with this is it's abrupt, it's hard to predict, and it can often have fog with it. So if you're out on the water and you don't have good navigation, or there's some other thing going on, you can lose it. You're in the fog, you can't see anything. So it's really an issue. I've got a couple pictures here. That's that same one on the right. One of my colleagues happened to be coming back from Hawaii and took a picture of one of these little spots here, Cape Lookout. You can see the line of the cloud and the clear conditions on the beach, and then the fog moving in. Thought that was kind of a neat little picture. And then if it really gets, if the marine layer really gets a relaxation event, then the north winds will die almost completely. And if you get westerly winds, then all that stratus that forms out over the cool water will blow into the valley, and that's what's shown here. We call that a marine push. If it's been a hot, like last summer when we had those heat waves, this was really nice to have a marine push, because you might have a temperature change from 90s to upper 60s in a few hours, and feels pretty good. The air conditioner turns on and pours right through the valleys. And that's what's shown here, these clouds that come in quite often when you get a marine push. Okay, so I'm going to jump to the last topic I was going to look at, which is large scale effects. And we're going to talk a little bit about El Nino, and mostly about La Nina. And the reason that we have a strong La Nina this year, and I keep an eye on it just because I kind of want to know more about it. How does it affect our weather? Does it affect our weather? I'm showing you a couple plots here, and I got both of these from, there's a NOAA website called the CDC Map Room, and you can see SST plots and things like that there. And this is showing you the weekly sea surface temperature anomaly. So it's showing you where the water is colder than normal or warmer than normal. And you can really see La Nina right now, maybe not, right in this whole Central Pacific, where temperatures are roughly 1 degree to maybe almost 2 degrees below normal, really below normal along the coast of South America. Okay, so this is a signal of La Nina. On the right side, I'm plotting, or they plot the average anomaly between 3.5 north and 3.5 south. So that's this little zone across the equator, all the way across the equator. So here's 135, that's way over here. Basically, this would be the eastern, let's see here, the Eastern Asian, Philippines, all those areas. And then the date line is at 180, that's this dash line. And then here's that cool water. So that's the where we are location wise. And then time goes basically down. So today is at the bottom, a year ago is at the top. And so what we're seeing is how the La Nina evolved over the past year. And the first thing you can see right away is the last May, there was nothing going on, right? There's no positive anomaly, there was no negative anomaly. That persisted all the way until the middle of September last summer. We call that La Nada, because there's nothing going on. And that's just sort of what the term has been coined for that. And there's, it probably had something to do with the hot weather we had last year. All right, so from about September until, I'm going to say sometime in March, things were progressing such that we had a La Nina during the winter, and it looked like it was about done. Right here in March, it started warming up in the Western Pacific, and the Central Pacific was kind of cool, still cool, but not really really strong. And I think the Weather Service or NOAA or somebody came out and said, well, we think we're going to go into another La Nina like we did last year. It's all going to just go away. Well, it didn't, and instead it got cold again. And this is all the way across now where we are right now. So right now it's about the same place it was back in December and November in terms of how strong it is. That's pretty strong for this time of year. Typically it isn't, you don't have much signal in the summer, and that's a pretty strong signal. So here's another way of looking at this data longer term. So now we again have the entire tropics here, from 40 east, that's the Indian Ocean way over here, all the way to our west coast. And what I'm showing now are those temperature anomalies over the past, since the 1992. So it goes pretty far back in time. And I've kind of indicated a couple times when we had La Nina springs. One was in 2008, another one was in 2011. The last few La Ninas have been weak, and they've ended fairly quickly when we got into summer. So I call those La Nada springs down here just to give you some contrast to the La Nina springs. And I'm going to show some data from Salem. And what I'm showing here are the high temperature, low temperatures for each day. And the year goes across the bottom there. And this starts in the fall and goes through the summer. So it's what we call a water year, because we get most of our precipitation in the winter. So the plots show basically when we start getting precipitation until summer. So it goes kind of different than a calendar year. And winter is right over here where the lowest temperatures are. This is this spring. You can see that, it wasn't too bad back in March in terms of anomaly. If you look at this green area, that's normal. So the normal high would be where the green and red intersect there. As soon as you got into April, we got cold. And that's when that La Nina started kicking back in again. Okay, maybe there's some kind of relationship there. Whenever you see a lot of green on these plots, especially for the high temperature, that typically means we're having rain, we're below normal. So I'm going to look at a couple of other years here. So here's 2008. You see a lot of green. I put a box around the springtime period. It was definitely cold, except for this 1 week here where it really got hot and we broke some records. I mean, just thrown in randomly. Okay, and then it went right back to what it was before. We really didn't get nice weather until into the end of June. 2010, 2011, it stayed cold pretty much the entire spring and went into the summer. It didn't really stop being La Nina conditions until what I call La Nina conditions until August. And also the rain there was a lot of precipitation. That's what the bottom plots show. Okay, what about the La Nada years? La Nada years were warm, no doubt. You can look at both of these springs. They both show well above normal. That's last year. That's kind of insane there when we had this heat wave. But the main message here is that it looks like La Nina springs are typically going to be below normal. And I do put a caution up here. We have to be really careful because we're really only looking at a few years. And there's this tendency, and meteorologists have a tendency to say, wow, look at that. Those must be connected somehow. And they might be, but it's not something that I think that you want to say every year we get a La Nina condition, we're going to have West Coast cold and lots of rain in the Northwest. But anyway, so I'm going to close on that and open it up for questions.
Thanks, Eric. Very, very interesting stuff, and really appreciate you putting this together for us. I got a couple of quick questions before we start taking some here. So your sea breeze fronts, what typically, are there certain places in the country where they push in really far inland? And then you've seen that happen. And then like the coast of Florida, you could have a sea breeze front on the east coast. Could you have simultaneous Gulf and Atlantic at the same time, resulting in convection in the middle of the peninsula.
Yeah, yeah, you can. I mean, in Florida, I'm not real familiar with it, but so much of the sea breeze is dependent on what the large scale flow is, and you want weak large flow conditions, right? If things are like here, it's true. If you have strong flow, it dominates over what's happening locally. So you want kind of not a whole lot going on. In Florida, I'm sure that's the same story, right? Because I imagine you have sea breezes pretty much all of our coastlines at some point in the year.
Okay, thanks. And do you know, as far as places where it pushes really far inland?
Maybe this is a bit extreme, and maybe it's not really a sea breeze, but actually in the state of Washington, I used to live in Eastern Washington, hundreds of miles from the coast, and we would get occasionally we would get what I will call a sea breeze. The wind blew basically all the way from Puget Sound, all the way down the mountains, all the way to Richland, Washington, it was just following the terrain.
Wow.
So yeah, it can go a long ways inland if it's strong enough and if there's enough density difference.
Great. Well, thank you. Well, let's take a couple questions.
Hey, Henry, actually, this is Noah at headquarters here. I want to ask a question of mine as you're organizing really quick. One for me, and then I also have a question from Nolan, our founder for CoCoRaHS. He's got a question that I'm going to field as well. But Eric, really quick, in a couple of your slides, and I wondered if any of your modeling has looked into one of my favorite effects with wind and clouds is the von Karman vortices. There were a couple of images where it seemed that there were some, and I'll encourage our listeners to Google that and look at that. And it's my understanding that usually comes from not necessarily a cape, but more of an island in the middle of the ocean. But I'm wondering if any of your modeling has ever demonstrated those von Karman vortices off of a cape.
That image I showed there, you could probably, I think they're basically some of the same fluid dynamics going on there. You have to have a shallow boundary layer and stratified enough so that it's perturbed, and so you could be seeing half of a von Karman street with the capes. I'm not going to say 100% that I know for a fact that's what it is, but there's a lot of similarities in the flow setup. So.
Very cool. Thank you. And then my last question, it's on behalf of Nolan, who is watching, and he wanted to know about last summer, the heat wave that you guys experienced there and why the sea breeze failed to provide any sort of cooling.
The flow was very strong offshore in terms of the large scale flow was pushing the heat wave went all the way out into the ocean. Last summer I went over to Newport after that heat wave, and there were trees, cedar trees and Doug fir that were burned from that heat wave. They had never, basically what it tells me is that those trees had probably never been exposed to that kind of heat. It got to over 100 degrees in Newport for 2 or 3 days. It was just I will call it an unprecedented event. I don't know if it's happened. It hasn't happened in our kind of recorded meteorological history. It was very unusual. So sea breeze could not overcome that. It was strong offshore flow.
Wow, thank you very much. And I'll turn it back over to Henry to field some questions now.
Mm-hmm. Yeah, great. And here's one of the first ones we got with your fishing picture. Nancy wanted to know, were those Dungeness crabs you were catching out there? And I assume that's it, right?
Yes, Dungeness crab.
There we go. Okay,
yeah, that's what we target those, and you also get rock crabs, but typically they're smaller, so we don't keep them.
Gotcha. Catherine was wondering, how do sea breezes affect the jet stream? So do they get up that high? Is there any correlation there?
Not really. The timing for the jet stream is going to be something you're going to see with large scale storm systems, like right now in the wintertime. So it isn't so much they don't affect each other. It's just that if you have the jet stream, it means you've got strong fronts and strong gradients, which means that the sea breeze is going to get overwhelmed more than likely by the weather. And they're also, you know, in the vertical, the sea breeze is shallow compared to, say, a jet stream, which is at aircraft height, 30,000 feet. And the sea breeze is shallow, maybe up to 3,000 feet, 4,000 feet.
Okay, here's Rick writes, and he lives in Southern California. He wants to know what strong northwest surface winds they allow for the nutrient-rich deep water to rise up, giving us red tide. Is that true? Is that what happens there?
Yeah, when I was just saying that you get these balloons, that's correct. You can get different kinds, but if you get the wrong well, I should say the right conditions, you'll get types of phytoplankton or whatever that can give you a red tide. There's probably maybe more to it down there. I'm not real familiar with it, and I'm definitely not a marine biologist, but you're adding nutrients, you're giving the microorganisms food. So here on the coast up here, what happens sometimes is you'll get strong upwelling, it will relax, and then all the microorganisms that are essentially munching on all that food, they die. And then when they die, they sink to the bottom, and then you can get conditions that are sort of detrimental, apoxic. The oxygen levels go way down, and then like crabs and things like that can't survive. So it can have a really big impact on both ends when it's occurring and then after it's done.
Okay, we've got some more questions. Looks like a lot of folks from Oregon and the West Coast here writing in right now. Jeff wants to know, he said the last 8 years he's lived just southeast of Portland in Happy Valley at about 600 feet. He was very surprised the amount of small hail that they received, mostly in winter. Could you explain why they get so much?
You know, those convective showers that we were looking at, and this winter, because it was La Nina, we had a lot of flow conditions like we have right now. Those convective showers can create or can produce small hail, and often will. And it really has a lot to do with whether or not we're getting that strong convective cold air aloft, which we had a lot of this year. And that would be my explanation as to why you might have noticed a lot more recently. We've been having La Ninas during winter for the past 3 winters. So it's been the summers that have been not La Nada, except for this year. And I don't know what'll happen for this summer, but I doubt that we'll see a repeat of the heat that we had last year. I mean, based on what I'm seeing right now, it should be more of a normal kind of summer.
Okay, Kevin writes in, and he wants to know, what can you say about monsoonal flow from the southwest affecting precipitation in the Pacific Northwest?
Okay, so occasionally, again, it's kind of rare, but occasionally we'll get a trough. And when I say trough, I mean a upper level disturbance that extends down off the coast of California. It'd be really weak. This would be in the summertime. And when those happen, occasionally you can get southwest flow or southeast flow that goes from the desert southwest all the way up here. And if that happens in like August or the time periods when there's tropical moisture over Arizona, it can draw that into Oregon. And when it draws that in, we'll get convection. We'll get thunderstorms like they get in Arizona. Not so much like the ones I showed there a minute ago, but we can still get actual thunder. It's kind of rare, but that's how we get a lot of, if we're going to get a thunderstorm in the summer, it's going to come from some of that monsoonal moisture making it north, more than likely. So that's a good question, because it is one of our only ways to get like an inch of rain and thunder and lightning here.
James lives in California. He wants to know if you could talk about, are there triggers for Santa Ana winds, if you know anything about that? Yeah,
Santa Ana winds, you know, and here again, there's been a couple of fire events in California, which were up north. And when you get in the fall, in particular, when you get the transition from summer to winter, you will get stronger high pressure systems over Canada, mostly because you're cooling the air and you're getting more, you just get stronger high pressure systems. And if you get the right setup, those can move south. And if they move south over the Rockies or over the Intermountain kind of west, that high pressure system will can generate really strong downslope winds anywhere along the west coast. Okay, the Santa Ana is the furthest south extension of that. When we had all those fires here in Oregon a couple of years ago, that was like a Santa Ana event here over our Cascade range. It's basically, the setup is to have a strong high pressure on the east side of things, sliding south, and that gradient between that high pressure and right over the mountains will provide essentially the energy for those Santa Ana winds or any of those strong downslope windstorms.
Okay, we're just going to take a couple more questions here, and then the rest we're going to see if Eric can follow up with you guys by email. Sherry wants to know if why does La Nina come with more rain in the Pacific Northwest but less in the San Francisco Bay Area, if that's true?
That's a good question. And so without going into too much about how we think, and we is not me, because it's mostly other people who study tropical interactions with mid-latitude storms. We think that what sets it up is the cooler water over the Pacific changes where you have convection over the Pacific. And that convection, much like the convection here, it's basically injecting energy into the atmosphere. And then what ends up happening is you'll get a wave set up from where that convection is occurring that propagates over the pole. So that, and this is large scale, this is like, planetary scale wave. Depending on where that happens, you can have regions of low pressure that are sitting in a spot semi-permanently adjacent to places where there is not low pressure. So right now, the way it's set up is it's the low pressure is sitting in the Gulf of Alaska, and it's a higher pressure down in California. And that setup is basically keeping everything up here, and not, especially this late in the year. But even in the winter, California got pretty much missed out because everything was always up here. It didn't ever get south. And I think that's probably the easiest way to describe it. Again, I don't study that kind of stuff myself, so I'm not probably the best person to answer the question.
Okay, we'll take one more question for today. And this one here was from Cheryl. She was wondering, have you correlated La Nina spring with any rainfall? She's in her third year of subnormal rainfall. Southwest Oregon in the Illinois Valley is where she lives.
There again, I haven't personally done work on that, but this is all my looking at those charts that I showed you a little while ago. There's a pretty strong gradient in rainfall depending on where you are north-south. So it's for the northern, like up here, Seattle, I think there is a positive correlation. We get more rain in La Nina winter and spring. As you go into California or towards California, that drops off. And where that line is, I don't really know, but I think there is probably some relationship there. Yeah, I mean, the area down in Southern Oregon, there's also just a long-term drought going on. And, I don't think anybody has a real good understanding of that, and or whether it's related to climate change or what, but things are definitely drier as you head south, and that's a long-term trend.
Okay, well, one more question here. This is an easy one, a quick one. Rick wants to know, does Oregon State have any wind and temperature sensors along the Oregon coast, particularly at Yakuts? Is that how you pronounce it?
Yahats.
Yahats. Okay.
We don't. I don't know what, occasionally there'll be temporary things that are put out there for various reasons, but, I don't know of anything that Oregon State is placing on the coast as far as weather data. Most of the research that's done over there is oceanographic and things like wave data and stuff like that you can get. Also what weather data I do know about is at Hatfield. It's up in Newport. So I don't know about down by Yahats.
Great. Well, Eric, thank you again. And again, folks, Eric will follow up with you in the next couple of weeks with your questions. We'll send those to him that we weren't able to answer today. But Eric, thank you. Very, very interesting. I learned a lot today, and I'm sure our observers and participants did as well. So thanks, and appreciate you being with us.
Yeah, my pleasure. It was fun.
Well, folks, as we close out today's program, we want to let you know that information on our next Weather Talk webinar will be coming out soon. Check our website or message of the day for more details on that. And before I forget, when signing off today, please take that short survey that pops up on your screen. That helps us know how we're doing. Well, until we meet again, stay safe and healthy. This is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now and wishing you a good start to the summer season as that comes rolling around here shortly. Take care, and we'll talk to you later.